Welcome to the Explainer. You know, if you really stop to think about it, the human brain's adaptability is honestly mind-blowing. If I ask you to perform a totally brand new task, say sorting a list of words by their emotional tone, you probably only need a brief instruction or maybe one or two examples and you've got it. You adapt instantly. But for a long time, artificial intelligence, yeah, it couldn't do this. Today, we are exploring a massive paradigm shift in AI, diving into a landmark research paper from OpenAI titled Language Models Are Few-Shot Learners. This is the actual paper that introduced GPT-3 to the world and fundamentally changed how we interact with machines. All right, here is our quick roadmap for today's explainer. 1. The fine-tuning problem. 2. Learning like a human. 3. Enter GPT-3. 4. Crushing the benchmarks. And 5. The limits of scale.
Section 1. The fine-tuning problem.
So, to really appreciate the leap GPT-3 made, we first have to understand the major bottleneck that absolutely plagued natural language processing systems for years. Think about this question for a second. How many examples do you actually need to learn a new task? Like we mentioned earlier, humans are ridiculously efficient learners. You don't need to see 10,000 examples of a translation to understand how to translate a simple phrase if you already know the rules. You can seamlessly switch between speaking, doing arithmetic, and critiquing a story without missing a beat.
Well, compare that human fluidity to the traditional paradigm in AI, which is known as pre-training plus fine-tuning. In this old-school approach, a model is first trained generally, but to get it to do a specific task, like reading comprehension or translation, you have to fine-tune it. And that means literally updating the model's underlying mathematical weights using a narrow task-specific dataset of thousands, sometimes hundreds of thousands, of labeled examples. I mean, it's just incredibly impractical. It requires massive data collection for every single new trick you want the AI to do, and it results in a model that is overly specialized and super rigid.
Section 2. Learning like a human. The researchers at OpenAI basically wanted to bridge this massive gap. They wanted to create a system that possessed human-like fluidity, allowing it to rapidly adapt to a new task without needing a massive new dataset. So the absolute game changer here is this concept: in-context learning. This is the magic behind GPT-3. Instead of retraining the model's architecture by updating its weights or gradients for every new task, you simply use the text input itself to tell the model what to do. You just provide natural language instructions or a few examples right there in the prompt, and the model predicts what comes next based on the broad pattern recognition skills it already developed during its initial training.
In traditional fine-tuning, you have repeated gradient updates, lots of heavy lifting across tons of examples just to change the model. But with in-context learning, zero gradient updates. The model doesn't change its internal weights at all. You have zero shot, where the model just gets a natural language description, like translate English to French. Then there's one shot, where it gets the description plus a single example. And finally, few shot, where it sees a handful of examples before being asked to complete the prompt. It's learning on the fly, entirely within the context of the conversation.
Section 3. Enter GPT-3. Now, the idea of in-context learning had definitely been tested before, but it was previously far inferior to traditional fine-tuning. What finally unlocked its true potential was an unprecedented, massive leap in scale. 175 billion. That is the jaw-dropping number of parameters, the neural network connections inside GPT-3. To put that into perspective, this autoregressive language model is 10 times larger than any non-sparse language model that came before it. The researchers hypothesized that if a model is just big enough, its ability to absorb diverse skills and recognize patterns during training would naturally make it an incredible in-context learner. And when they tested this hypothesis by tracking accuracy on a simple task, the results were stunning. A smaller, 1.3 billion parameter model barely improves at all as it sees more examples, but the 175 billion parameter GPT-3, the performance curve is incredibly steep. As parameter count scales up, the model's ability to actually learn from those few examples provided in the prompt increases dramatically. We see this trend broadly across all 42 benchmarks tested in the paper. As model capacity increases, the overall performance goes up smoothly. But what's really fascinating is the massive growing gap between its zero-shot and few-shot performance. As capacity scales, the few-shot performance just rockets upward much faster. This strongly suggests that larger models are fundamentally better meta-learners. They aren't just memorizing better, they're actually getting better at adapting to new tasks on the fly. Of course, to feed a synthetic brain of 175 billion parameters, you need an unfathomable amount of data. The 45 terabytes of compressed plain text data used to train GPT-3 relied heavily on a filtered version of the Common Crawl, which is basically a massive scrape of the internet. That made up about 60% of the mix. But to ensure high quality, the researchers intelligently balanced this web scrape by sampling more heavily from curated datasets like books and Wikipedia. They essentially gave the model the entire internet to read, but made absolutely sure it paid extra attention to the good stuff. Section 4. Crushing the benchmarks. Let's look at exactly what happened when they unleashed this massive few-shot learner on standardized AI tests without allowing it any specific fine-tuning. Take Trivia QA, for example. This was a true David versus Goliath victory, but kind of in reverse. Open domain systems, the previous state-of-the-art, are allowed to use information retrieval to search through millions of documents to find answers, scoring around 68%. GPT-3, however, was evaluated in a closed-book setting. No searching allowed. It had to answer trivia strictly from the knowledge baked into its 175 billion parameters. And yet, simply by seeing a few examples in the prompt, the few-shot GPT-3s scored 71.2%, actually beating the state-of-the-art systems that were specifically fine-tuned and had access to a search engine. That is wild. Then there's the Lambda benchmark, which tests a model's ability to understand long-range dependencies in text, basically predicting the final word of a long paragraph. Prior to GPT-3, researchers genuinely thought we were hitting a wall on this test. But by simply framing the prompt as a fill-in-the-blank exercise with a few examples, GPT-3 absolutely dominated. It achieved an 18% increase over the previous state-of-the-art. When it comes to language translation, GPT-3's training data was 93% English, so it was heavily skewed. But despite that, when translating into English, like French to English or German to English, few-shot GPT-3 consistently outperformed prior unsupervised translation work by a massive 5 points on the blue scale, which is a standard metric for evaluating translation quality. It achieved this just by being shown a few examples of translated pairs right in the prompt. Beyond the standard benchmarks, the researchers also threw some synthetic, highly qualitative tasks at GPT-3 to test true on-the-fly reasoning. They asked it to unscramble heavily manipulated words. They asked it to perform 3-digit arithmetic. They even gave it a fake, totally made-up word, defined it once, and asked the model to use it in a new sentence. And surprisingly, GPT-3 showed clear proficiency. It was rapidly adapting to synthetic tasks it was highly unlikely to have ever explicitly memorized during its internet training phase. Section 5. The limits of scale. Now, as enthusiastic as we can be about these breakthroughs, to really understand this paper, we have to look objectively at where this few-shot paradigm shift currently falls short. Because scale is not magic, and it doesn't solve everything immediately. The researchers were very clear about where GPT-3 struggles. For one, it performs close to random chance on some natural language inference tasks, which test if one sentence logically follows from another. It also struggles with complex reading comprehension datasets like Quack, which involves modeling teacher-student dialogues. And on a test called WIC, which asks if a word is being used with the exact same meaning in 2 different sentences, GPT-3 was basically just guessing. This proves that while scale brings incredible pattern matching, it doesn't instantly solve deep comparative logic or complex structural inference. Another major limitation noted in the paper is a methodological challenge called data contamination. Think about it. When you train a model on 45 terabytes of the internet, there is a very real risk that the standardized tests you use to evaluate the AI are already floating around somewhere in that training data. The model might have inadvertently ingested the test sets. While the OpenAI researchers systematically measured this overlap and found it had minimal effect on most of their results, they impartially acknowledged that this is a growing and serious problem for validating high-capacity AI models going forward. Finally, the paper steps back to impartially observe the broader societal impacts of a model this powerful. They ran an experiment having GPT-3 write synthetic news articles from a single prompt. Their conclusion is pretty striking. GPT-3 can generate samples of news articles which human evaluators have difficulty distinguishing from articles written by humans. The researchers openly state that this raises serious questions about the potential misuse of language models for things like misinformation and spam. It's a powerful reminder that with massive technical capability comes a vital need for careful societal reflection. And that leaves us with this final thought. The GPT-3 paper proved that massive scaling, combined with in-context few-shot learning, completely shatters the old requirement of needing thousands of examples to teach an AI a single task. We are moving closer and closer to machines that can fluidly adapt just from reading simple instructions. So as we look at the success of 175 billion parameters, what does this actually mean for the future? If simply making the model larger unlocks this much human-like adaptability, what happens when we scale to 1 trillion parameters and beyond? Will we eventually reach truly general-purpose AI, or are there hard limits to what scale alone can achieve? Keep that in mind as you watch the AI landscape evolve. Thank you for joining me for this explainer, and keep learning.